Hello, my name is Michael, and my goal is to help you introduce and nurture math skills using number knockout games. Number Knockout is a game detailed at nationalnumbernockout.com. It's ultimately an annual national competition, but the game can be used in many forms to develop math skills at home, with friends, and in classical conversation homeschool communities. The challenge often faced is that N2K, as it's nicknamed, is competitive, but homes and communities often want to employ the ingredients of the game in cooperative and educational ways. The purpose of this video is not to detail the many variations people have invented. Neither is the purpose of this video to train N2K champions. Rather, the purpose of the video is to take tutors and teachers progressively through the skills to introduce and nurture in your students. These math and strategy skills can be developed in an environment of self-competition or in cooperative ways in class. The skills treated by the end of this video are advanced. There's a tremendous divide between the beginner's ability to make progress on the board using basic math skills and strategies and the expert's ability to decimate the board in very little time, regardless of the roll of the dice. Number knockout games require a simple playing board like this, and dry erase markers, and 3 dice. Games start with a roll of the dice. The 3 numbers rolled are used by each player to build expressions that evaluate to unique numbers. When 1, 2, and 3 are rolled, a student is first likely to think 1 plus 2 plus 3 equals 6. Thinking he's exhausted his only easy option, the novice student resigns himself to trying subtraction. 1 plus 2 minus 3. Oops, 0. 2 plus 3 minus 1 equals 4. Hurrah! And 3 plus 1 minus 2 equals 2. Yay! At this point, many novice students might glance at a second or third year neighbor and discover that she's crossed out the entire top row of her board. With a dropped jaw, he'll wonder if he'll ever be as smart as that. But then he'll screw himself up to consider multiplication as the next necessary evil. 1 times 2 times 3 equals 6. Oops, already got that. How about 1 times 2 plus 3 equals 5? Aha! And 1 times 3 plus 2, same thing. But at this point, the student is already trying to process the numbers in a deterministic way, considering a pattern and its variations. This is a huge concept that we'll focus on soon. First, after a couple of warm-up games and some encouraging words about how younger students will soon learn how to be as productive as older students, you should consider a boardless game. For this game, just have the students write down their expressions in full on lined paper and not worry about crossing the numbers out on the board at all. This results in a much feebler release of endorphins, but it is effective in a way that we'll see right now. Let's consider our 1, 2, 3 example again. A young student might try 1 plus 2 plus 3, 1 plus 3 plus 2, 3 plus 2 plus 1, and perhaps it doesn't take quite so long to give up on this tack and realize that the order of the added numbers is not going to produce a new sum. This is fine. They're just reinforcing the commutative law, which states that a plus b equals b plus a. This is a good thing, and even if a student is trying many expressions that result in the same answers, encourage them. Soon a student will scratch out something less random, like 3 plus 1 plus 2 equals 6, 3 plus 1 minus 2 equals 2. 2 times 3 plus 1 equals 7, 2 times 3 minus 1 equals 5. Still, the student begins to feel that these numbers are very limited. He's not interested in trying division and is probably smart enough to realize that that won't help anyway. He looks at his neighbor and sees that she's filled half of the page and wonders, what's the trick? At this point, you'll be tempted to introduce powers, which we'll discuss soon. But you'll want to play several more games, mostly with boards and with rolls of the dice that allow the student to produce more interesting sums. The patterns that they'll employ will look much the same, and though the solutions will target numbers further down on the board, the overall impact on the board won't be much more impressive. Remember, a normal game involves the student's mental arithmetic skills. Students will not normally be writing their expressions, but there's nothing wrong with encouraging or requiring them to write the expressions out sometimes, to learn and to grow, and to refrain from writing them at other times. Okay, to maximize the impact of this training, we're going to continue to consider just those three numbers, 1, 2, and 3. Because of your adult ability to consider those numbers systematically, you're now thoroughly convinced of their limitations if you limit yourself to the 4 arithmetic operations of addition, subtraction, multiplication, and division. You're now ready for power. The power of powers, that is. And 2K allows any power to be applied to any number rolled. And tell your class that you'd like to do an exercise together. Write this on the board. 3 squared times 2 times 1 equals 18. You're suddenly in a new game. Of course, it's tempting to take this too quickly. You've already lost some students. First, it's important to note that I don't like starting with 2 squared, because that means 2 times 2, which is understandably confusing. Rather, start with the number 3 and take your time to break this down and indicate that 3 squared equals 3 times 3 equals 9. That is, the 2 as a power means multiply 3 by itself 2 times. 5 squared means multiply 5 by itself 2 times. Tell the students to just watch this and write 5 squared equals 5 times 5 equals 25. 5 squared is not 5 times 2, which would be 10. 5 to the 4th is 5 times 5 times 5 times 5, a very big number. But we didn't roll a 5. Let's go back to our real numbers, 1, 2, and 3. Again, we reflect on 3 squared times 2 times 1, which is 18. Now let's use this example to introduce or further develop the student's inclinations to a systematic approach. Let's call 3 squared times 2, or 9 times 2 equals 18, the target. What are all the things that we can do with our 1 at this point? Write the target expression 3 times, like this. 3 squared times 2, 3 squared times 2, 3 squared times 2. Then, entertain the possibilities from the class. Sure, you have times 1. That was the first example. What else? Of course, plus 1 and minus 1 follows from there. Without having to reevaluate 3 squared times 2, you've just crossed out 3 numbers, 17, 18, and 19. Now, write down a slightly different target. Again, 3 times. 3 squared plus 2, 3 squared plus 2, 3 squared plus 2. Again, what can we do with the remaining 1? Easy. We just did it. Times 1, plus 1, minus 1. We just knocked out 10, 11, and 12. At this point, the student who's been following and understanding is looking at the board with his jaw dropped. He now sees the light. Note that he's learned 2 big and important concepts. First, how to use powers to hit bigger target numbers, and second, how to consider variations on an expression in a systematic way, rather than randomly trying whatever next pops into his head. Most students will quickly see the power of not having to evaluate a long expression like this from scratch over and over. It seems like cheating to be able to apply times 1, plus 1, and minus 1 in order to get 3 numbers in one fell swoop. Some other students may be looking at you with dropped jaws rather than at the board, as if to say, "What are you talking about? I lost you when we wrote that tiny 2 above the 3. This is fine. This indicates that there is value in learning this new arithmetic skill. The introduction and practice of powers at home has now been inspired. A student slow to understand powers or slow with their math facts in general is likely going to face some discouragement here and should be loved and encouraged in his journey. It's worth pointing out at this point that it would be tempting to move on with your students, as I will in a moment, but consider camping out here for a while with your class. Whatever you do, try a few other things. For instance, practice some skip counting together, which should be accessible to all. Use some entirely different game to mix things up, and strongly consider ways in which you can encourage self-competition and kindness. Cooperative games can encourage kindness, and I'll get to an example of one in just a moment. First, however, I'll treat a simple technique for encouraging self-competition. Consider starting your next class with 3 quick games in a row. Keep each game to 1 minute. When everybody is ready with laminated board and whiteboard marker, have 3 well-behaved students roll the 3 dice. Write the numbers on the board and quickly say, "Go." Turn the hourglass or start the timer. Announce when there are 15 seconds remaining. Say, "Markers down" when the minute is up. Many students are a little stressed and several are a little discouraged by the few numbers that they were able to get. Throw in a quick word of encouragement, tell everybody to leave their marks, don't erase a thing yet. Everybody rotate markers and dice clockwise around the room, and then start again. 3 new rollers, 3 hopefully new numbers, and a ready, set, go. Tell the students to mark the solutions that they find, even if the number is marked already with their old color. Leave the old color, mark the new, either by circling or using a different direction or shape. 1 minute again. Done. Finally, do it one last time. Rotate markers and dice. New marks with the new marker color will now make a colorful board. Finally, have the students tally up their first color and then their second and then their third. Have them compare. Most of the time, especially with a very little graduated assistance from mom or dad beside them, students will improve a bit from rolls 1 to 3 and celebrate this. This whole exercise should be quick and high energy. Encourage everybody to erase their boards shortly after they get their tallies. The focus was to be on their own improvement, not on their performance compared to their neighbors. Encourage that observation of each student's own improvement. Occasionally, this won't hold up, but whether the student is very advanced and almost completing the entire board each time within the minute, or very novice and barely making 3 to 5 numbers each time, there's usually at least a slight improvement. Encourage the students to realize that practice makes us faster and makes our jobs easier, and all students will discover this over time. Move on quickly, again, staying ahead of the students and their temptation to compare with one another. If comparison between students arise, go ahead and mention, yes, some of you are very good at this, and the rest of you will become much better over the weeks and the years to come. You'll amaze yourself and your parents, and many of you will actually be better at this game than your moms and dads by the time you're third-year students. Now for a word about cooperation. If you have first-year students together with third-year students, consider a variation on this game where you use half boards. The first-year student gets the board with 1 through 18, and the third-year student gets the board with the remaining numbers through 36. Have each first-year student pair up with an older student, and consider orchestrating these pairings beforehand, and assign students to move to pair up according to your discretion. Remind students to be kind, not only to their partners, but also to themselves and to the others in the room. Then, play a game or 2, or 3. Older students will either focus on their own half and try for a good score by doing so, or they'll decide to be helpful and help the younger terminate their board. With an adult assisting and encouraging balance, cooperation and kindness can win the day. Again, consider playing a few games and try to score higher on subsequent games. discourage too much competition between teams, but because of the pairings, it's likely that no one team will dominate much anyway. Okay, let's get back to the hard math. The two skills honed in the last round were those of powering numbers and treating expressions systematically. Our last set of expressions was 3 squared plus 2 times 1, 3 squared plus 2 plus 1, and 3 squared plus 2 minus 1 for our 11, 12, and 10. Let's consider powers a little more thoroughly now. Write these on the board. 3 squared equals 9. 3 cubed equals 3 times 3 times 3, or 9 times 3, which is 27. 3 to the fourth power is 3 times 3 times 3 times 3, or 27 times 3. Whoa, that's off the board. Never mind. So we see that for the number 3, the only really valuable powers are 3 squared and 3 cubed. Let's consider 2's now. 2 squared is 2 times 2, or 4. 2 cubed is 2 times 2 times 2, which is 8. 2 to the fourth power is that 8 times 2, which is 16, and 2 to the fifth power is that 16 times 2, which is 32. And that's going to be as high as we can go for the regular N2K board, but that's a lot of targets. Remind your students that all those targets are legal, no matter what numbers are rolled. If you roll a 2, 5, and 6, all of the above are still legal. Now let's consider our proverbial roll of 1, 2, and 3. Again, but with our 2-power targets now. Let's take 2 squared plus 3 times 1 equals 7, and 2 squared plus 3 plus 1, 8, and 2 squared plus 3 minus 1, which is 6. 2 squared times 3 times 1 is 12, 2 squared times 3 plus 1 is 13, and 2 squared times 3 minus 1 is 11. 2 cubed plus 3 times 1 is 8 plus 3 times 1, which is 11 again. 2 cubed plus 3 plus 1 is 12, and 2 cubed plus 3 minus 1 is 10. 2 cubed times 3 times 1 is 8 times 3 times 1, which is 24. 2 cubed times 3 plus 1 is 25, and 2 cubed times 3 minus 1 is 23. And so far, we've only considered expression patterns where the 1 comes last. And consider, in parentheses, 2 squared plus 1, and then times 3, which is 15. 2 squared plus 1 plus 3 is 8, and 2 squared plus 1 minus 3 is 2. There are plenty of others, but there's no need to dwell too much on these variations, especially this first one. I offer 2 reasons. First, the student is now getting it, and let them develop it further. Second, our future strategies center around the idea of hitting a target and then hitting 4 or more numbers immediately around that target using simple addition and subtraction. All by itself, this strategy will help a student cover a board pretty thoroughly. We still have another concept to introduce before we can get there, though, but we're on our way. It's worth taking a short detour, though, and talking about order of operations and parentheses as they showed up in this last example. Your opportunity to consider order of operations and parentheses in class will pop up unexpectedly, so be prepared. Keep an eye out for those opportunities and understand things well enough to be able to make them teaching moments. The basic rule of order of operations is that multiplication and division must be done before addition and subtraction. Some remember this by a first letter mnemonic MDAS, MDAS, or my dear Aunt Sally. And so, for instance, 7 minus 2 times 3 requires that the multiplication of 2 times 3 be done first. The result, 6, can then be subtracted from 7. It's great to do some quick upside-down pyramid exercises in class. Write a long expression on the board, like this: 5 times 4 plus 3 times 2 minus 6 times 3 plus 8 divided by 2 minus 2 times 4 times 3. Then ask your class to evaluate. Evaluate all of the multiplication and division morsels, carrying down the addition and subtraction signs and doing the addition and subtraction last, always left to right. The result looks like an upside-down pyramid, with the point, the answer, at the bottom. Students who get in the habit of evaluating in this way will be well on their way in algebraic equations later as they work to reduce equations and isolate variables. I mentioned the helpful mnemonic, MDAS, my dear Aunt Sally, but be careful. Some students can overinterpret this to mean that multiplication must precede division and addition must precede subtraction. This is wrong. The common misinterpretation, therefore, would result in 4 minus 2 plus 1 equal 1, because they would want to add 2 plus 1 first to get 3, and then perform 4 minus 3 to get 1. No, arithmetic must be done left to right, except where order of operations requires pre-evaluation. Addition and subtraction are really equivalent, and so must be evaluated from left to right. Now, this left to right concept isn't exactly true, but it is a helpful way to proceed at this level. The advanced student will discover that you could do 4 minus 2 plus 1 in a different order, but you'd have to keep the signs. And negative 2 plus 1 equals negative 1, and then 4 plus negative 1 equals 3. That's the same answer as the straightforward 4 minus 2 plus 1 equals 3, because the student was careful with his signs. Likewise, multiplication and division are equivalent, but the advanced student will quickly point out that they can be done in any order. 4 times 3 divided by 2 is the same as 4 divided by 2, and then multiplied by 3. But again, such a student must be careful to keep the operator with the operand, and keep the numerators and the denominators where they belong. 4 times 3 divided by 2 is not the same as 4 divided by 2 times 3. All of this is worthy math instruction, best suited for the home environment as a part of the student's normal math curriculum. For N2K, consider simply promoting a left-to-right movement and evaluating multiplication and division first, and then the resulting addition and subtraction operations second. Note that the longer form of the mnemonic is "Please excuse my dear Aunt Sally." And "please" corresponds to parentheses, and "excuse" corresponds to exponents. That is, parenthesized expressions should be evaluated first using the regular MDAS rule within the parentheses, and exponents should be evaluated next, before multiplication and division, which in turn would be completed before addition and subtraction. This level of treatment seems scary, but it really becomes easy with some practice. However, it simply doesn't come up much in N2K, so don't get stuck on it. Move on. Let's move on to the next level of targeting and destroying the N2K board. The next level of skill requires one new piece of knowledge. A, any number, to the power of 0 equals 1. What? Yep, it's true, and I'll prove it later. For now, just accept it. It doesn't matter what the number is. If you take it to the power of 0, which is allowed in N2K, the value becomes 1. This will become extremely valuable to us, and it is the last big skill remaining in our quest to complete entire boards. At this point, we're going to consider our targets as powers of 2. Remember, they were 2 to the power of 1 was 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th power is 16, and 2 to the 5th power is 32. Let's consider the last target first, 32. We've obtained that target with the number 2, roll only, since powers are free. So we have our 1 and 3 both available to work around that target. Consider this systematic use of the 1 and 3. 2 to the 5th times 3 to the power of 0 times 1 to the power of 0 is 32 times 1 times 1. Each of those taken to the power of 0 is 1. So that's 32. 2 to the 5th times 3 to the power of 0 plus 1 to the power of 0 is 32 times 1 plus 1, which is 33. 2 to the 5th times 3 to the power of 0 minus 1 is 32 times 1 minus 1, or 31. 2 to the 5th power plus 3 to the power of 0 plus 1 to the power of 0 is 32 plus 1 plus 1, or 34. And finally, 2 to the 5th minus 3 to the power of 0 minus 1 to the power of 0 is 32 minus 1, or 30. We just instantly and systematically knocked off 5 numbers, our target as well as both numbers immediately below and above our target. You can do this same thing for every single 2-power target. So for instance, 2 to the 4th is 16, so you can instantly get 14, 15, 16, 17, and 18. That's the target, 16 and 2 below and 2 above. But that's not all. In this bundle, we only took both modifying numbers, 3 and 1, to the power of 0. So we constrained ourselves. Consider these. Additionally, 2 to the 5th times 1 to the power of 0 plus 3, which is 32 times 1 plus 3, or 35. 2 to the 5th times 1 to the power of 0 minus 3 is 32 times 1 minus 3, or 29. Again, this pattern can be applied to every 2 to the n target. So for our 2 to the 4th grouping, we can add 13 and 19 to the cluster. We're wiping out whole rows of the board with very little effort. Students who learn this trick will knock off entire boards very quickly. Usually, there are a few sticky numbers that require a little more attention, but progress is generally very efficient. In these examples, you might have asked yourself why I took 1 to the power of 0 to get 1, since 1 is already 1. Why take it to the power of 0 to make it 1, needlessly adding an operation? The idea here is to suggest the pattern regardless of the numbers. What if, rather than rolling 1, 2, and 3, we rolled 2, 3, and 4? The same collection would present itself. 2 to the 5th times 3 to the power of 0 times 4 to the power of 0 is still 32 times 1, or 32. 2 to the 5th times 3 to the power of 0 plus 4 to the power of 0 is 32 times 1 plus 1, 33. And 2 to the 5th times 3 to the power of 0 minus 4 to the power of 0 is 32 times 1 minus 1, or 31. 2 to the 5th plus 3 to the power of 0 plus 4 to the power of 0 is our 32 plus 1, which is 34. And 2 to the 5th minus 3 to the power of 0 minus 4 to the power of 0 is our 32 minus 1 variation, or 30. In this case, we're using a 4 in the place of the 1, but since we're taking it to the power of 0, making it a 1, the result is the same. Note that with this roll, though, we'd additionally get 4 more solutions around the target rather than just 2 more. We get 2 to the 5th times 4 to the power of 0 plus 3, or 32 times 1 plus 3, 35. 2 to the 5th times 4 to the power of 0 minus 3, or 32 times 1 minus 3, 29. And 2 to the 5th times 3 to the power of 0 plus 4, which equals 32 times 1 plus 4, bringing us to 36. And 2 to the 5th times 3 to the power of 0 minus 4, 32 times 1 minus 4, bringing us down to 28. Actually, there are even more. 2 to the 5th plus 3 to the 0 plus 4 equals 32 plus 1 plus 4, which is 37 off the board. 2 to the 5th minus 3 to the power of 0 minus 4 is 32 minus 1 minus 4, which is 27. Then we have 2 to the 5th plus 3 plus 4, which is 32 plus 3 plus 4, or 39, which is off the board. And 2 to the 5th minus 3 minus 4, which is 32 minus 3 minus 4, that's 25. Now we've slaughtered the entire bottom rows of our board, except for 26, with just one target, 2 to the 5th. You can imagine the potential for slaughtering the rest of the board using other 2-power targets of 2, 4, 8, and 16. You could consider 3 targets if you needed to fill some holes. 3 to the first power is 3, 3 squared is 9, and 3 cubed is 27. You could combine those targets with the 2 taken to various powers, such as 3 squared plus 2 squared plus 4 is 17, 3 squared minus 2 squared minus 4 is 1. Great ranges can be achieved with this tactic. These can be very valuable when trying to complete an entire board or an alternative board, such as the odds board or evens board. And of course, power targets are essential to trying to complete a 37 to 73 board. We've now covered the bulk of the uses of the 2 major skills we learned: powering numbers and treating expressions systematically. Note that one of the major advantages to mastering these skills is the increased ability to reproduce a hit. When somebody challenges a student's number 30, for example, the student can quickly reconstruct. First, he used 2 to the 5th to get the nearby target of 32. And 30 is just 2 away from 32, so it must have been 2 to the 5th minus 3 to the power of 0 minus 4 to the power of 0. Even if 2, 5, and 6 were rolled, the student could quickly conclude that the 32 was hit by the same pattern: 2 to the 5th minus 5 to the power of 0 minus 6 to the power of 0. If the challenge floated was, how did you get 29? The student would have to think a little harder and finally come up with 32 minus 3, which is 2 to the 5th minus 3 times 4 to the power of 0. The student has grown to the point of doing all of this in his head, and rarely, if ever, needs paper to check arithmetic. The student is reinforcing basic math facts with numbers that exercise most of the skills used in all expressions, even with bigger numbers. You could, of course, introduce bigger numbers by introducing a 12-sided die or an n-sided die. You could use 2 dice or 4 dice for a challenge. But the expression that you can get out of a standard dice, standard game, standard board is extraordinary once you know the tricks. I should do 2 more things. I should cover one more advanced trick and simultaneously highlight a sticky point in the N2K rules, and I should prove that a to the 0 is 1. First, one more advanced trick. It turns out that students will quickly covet the number 2. They'll much prefer a 2 to a 6 or a 5, and they've come a long ways. In their novice years, they'd have preferred the bigger numbers like 5 or 6 in order to hit higher on the board, but now that they know the power of 2, when 2 is taken to powers. So, what if you don't roll a 2? Are you stuck? A 3 is good, but not quite as good as we've seen. Well, it turns out that a 4 is just as good as a 2. Here's why. You know that the square root of 4 is 2. Well, there's another way to express that. The square root of 4 is just 4 taken to the half power. And that's simply what a square root is. So you could take 4 to the half power and then to the 5th power, and you'd have the same thing as 2 to the 5th, your 32 target. However, technically, that would be breaking the N2K rules, which states that only one power can be applied to each number. This is not a problem because 4 to the half to the 5th is just 4 taken to the power of 1/2 times 5, which is 4 to the 5 halves. That may seem like a bit of magic, but it's not too far out there. Just look at that chain of equivalency a bit and you'll see it. 1/2 times 5 is just 1/2 times 5 over 1. And of course, 1 times 5 is the numerator and 2 times 1 is the denominator. And here you have 5 halves. You've just rolled the number 4. you've taken it to a fractional power, and you got the same thing as 2 to the 5th. Last but not least, let's prove that a to the power of 0 is 1. I'm not going to present a formal bulletproof proof here. Rather, I'm going to present more of a demonstration proof that's fairly easy to follow and very effective in helping a person see that a to the power of 0 is 1. We'll start with assigning a number. Let's use 2 for kicks, and let's work our way up, starting from 2 to the power of 1 is 2. 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, and 2 to the 5th is 32. Now, if we work backwards from here, you can see that the 32 divided by 2 yields the 16, the previous number. This is pretty obvious. We just reduced the power by one factor. If you do that again with the 16, you get 8. 8 divided by 2 is 4. 4 divided by 2 is 2. You see the pattern now. What happens next? 2 divided by 2 equals, 1. 2 to the power of 0 is 1. I hope you've enjoyed our time together, and I hope this makes your time with Number Knockout and your students more enjoyable too. It should give you a trajectory moving from the basic play of this game to much more advanced play. This will take time and shouldn't be rushed, but it does help to have a target in mind and to realize that there's more to the game than simply becoming faster with your math facts and more focused on the game. There's a systematic approach and some real arithmetic skills that can take you to unexpected places. Many blessings as you grow in your math journey with your students.